Okay, welcome to the lecture 52 in this course Classical Mechanics 1. In this lecture, we will start with the discussion the stability of circular orbit. So, in last class we have seen that by plotting the U effective for example, in a particular problem U effective with the various energies, for example, E greater than 0, E equal to 0, E less than 0 and E equal to the minimum of U effective minimum. So, all these cases we discuss qualitatively what will be the possible trajectories. Okay. So, we found that when the energy of the particle is equal to the minimum of the U effective potential, then we have a circular orbit. So, this gives to circular orbit. This E less than 0 possibly ellipse okay. So, this possibly it will ellipse and when E greater than 0. So, let me draw this because this pen was not working. So, this for ellipse, this is for E greater than 0 hyperbola E equal to 0 parabola and E less than 0 ellipse, and most interesting thing that we will concentrate today when we have E equal to we were discussing the stability of circular orbit and we found that when you have the energy equal to U effective minimum, then we have a circular orbit. And for that we U effective minimum was del L del R at some point of R equal to R0 is 0. But del effective del R equal to 0 is also a condition for maximum. For example, if you have a potential of this kind, then here also U effective del U effective del R will be 0 at some value of R0. So, now question we are going to address in this today's lecture is that when the circular orbit will be stable or where it will not be stable. Towards the last lecture we mentioned that we will consider for this purpose a generic potential or generic force field which is given by Fr equal to minus alpha r to the power n. So, let us write this is equation 1 and alpha greater than 0. So, M is to find the condition for stable circular orbit for this fold, for the central force given in equation 1. So, this is the idea is M. Okay, so let us perform this. So we have to make sure that the minima where del u effective del r equal to 0 has to be the true minima of the system. If it is true minima, then it will be a circular orbit. So for stable circular orbit, for stable circular orbit, so del u effective del r equal to r 0 should be 0, first condition, but this is also a condition for maximum. Then second condition, so it has to be the true minimum del 2 del u del r square at the same point r 0 should be greater than 0. That means at r equal to r 0, u effective will have a true minima to have a stable circular orbit. So we will find that in this case what will happen to that. Okay. So let us start. So our force F r is given minus alpha r to the power n. So let us calculate the effective potential. For that we need to calculate u r. U r is nothing but minus alpha 1 over r to the power n dr, right? Because u equal to minus, so this will be minus minus plus. Okay, u f equal to minus del u del r, so it will be minus and there is a minus. Okay, so r to the power minus n will have integration. So integration will add 1 power. So r to the power n minus 1 divided by n minus 1. So n minus 1 and here minus n plus 1, because r to the power minus n integration is r to the power minus n plus 1 minus n plus 1. So it is 1 minus n and it is minus n, this is also minus n plus 1. Okay. So your potential will be alpha 1 minus n r to the power 1 minus n. Okay. So this will be your potential. Okay. So your effective potential, so u r is this, so u effective will be u r plus, you recall, m square 2 mu r square. Okay. So this is your, so let us denote this is as equation 2 for today. Okay. And then let us find where this potential has a minima or maxima. For that, u effective del r, let us say at r equal to r 0, it will have a minima. So this will be and u r is let me write alpha 1 minus n r 1 minus n plus m square 2 mu r square. So if I differentiate, I will get alpha 1 minus n r to the power 1 minus n, so 1 minus n minus 1, so r to the power minus n. Okay. So this will be the differentiation of the first integration, so r 0 minus m square mu r 0 q, and that has to be 0 to have a maximum. So here let us find what will be the r 0. So first we can see this get cancelled. So alpha by r 0 to the power n minus m square mu r0 to the power 3 equal to 0. So, r0, if I rearrange, r0 3 minus n will be equal to m square by mu alpha. Okay. So, let me check whether I am writing correctly. So, r0 3 minus n will be m square mu alpha. Very good. Okay. Now, now we have to see whether this is a minima or maxima. That means we have to apply the second derivative to this and check whether second derivative at that point whether it is greater than 0 or not. Okay. So, let us differentiate this. Let us find del 2 del effective del r square first, and then I will put r equal to r0. So, if I calculate, first term was your r0 to the power n, alpha r0 to the power n. So, it will be alpha then minus n r0 to the power minus n. I have to differentiate. So, differentiate minus n and minus 1. Okay. Good. And then other term m square m mu. So, minus then r to the power minus 3. So, it will be plus 3 m square mu r to the power 4. No 0 here. I have not put 0. So, to the power 4. Okay. And now this has to be calculated u effective r square at r equal to r0. So, this will be minus alpha n r to the 0 to the power n plus 1, okay, plus 3 m square mu r0 to the power 4, and this should be greater than 0 for true minima. This we have, this you know. Okay. So, now let us simplify this and the condition. So, this is the equation, this is the equation 3. Let us denote equation 3 we obtain where the potential will have a maxima or minima. So, that point we will check double derivative is negative or positive. Okay. So, that r0 value we have to use, but before that let me simplify this expression. Minus alpha n r0 to the power n plus 3 m square mu r0 q greater than 0. I am just multiplying by r0 both side, right hand side is 0. So, there is no problem. Now, I will substitute equation 3 r0 to the power 3 minus n. So, if we multiply this equation further by r0 to the power 3 implies minus alpha n r0 3 minus n, I am multiplying by r0 to the power 3 plus 3 m square mu, okay, 3 m square mu r0 alpha n. Now, substitute r0 to the power n, r0 to the power 3 minus n. Now, substitute this equation, equation 3, which is nothing but m square mu alpha. So, implies minus alpha n m square mu alpha, I think correct, mu alpha plus 3 m square mu, okay, greater than 0. So, if I take common, so this alpha get cancel here, alpha get cancel. So, if I take m square by mu common, then I get 3 minus n should be greater than 0, and this can greater than 0 only when 3 is greater than n. So, we find a condition that n should be less than 3. is the condition that for the central force F r equal to minus alpha r to the power n will have stable circular orbit. So, this we found that under which condition, which value of n, the central force F r, which is minus alpha by r to the power n, will have a true minima. And when you have the true minima, if the particle has the energy equal to the true minimum energy, then it will have a stable circular orbit. On the other hand, if you look at this case, that recall the example 2 I consider in next class. Example 2, u r was minus alpha by r q, and in that case you recall your potential energy u effective curve was like this, and there is a possibility of circular orbit at the maximum point. Possibility of stable circular orbit at this point. However, you can check and also clear from the diagram, you can check this is not the minima of the u effective, which is in this case alpha by r q plus m square 2 mu r square. You can check yourself the minima value or maximum value. So, you will find this. So, this will not be. So, I urge you to check this will not be the stable circular orbit. So, this point we will spend more time when we will consider one more example in the context of this in the tutorial class. Okay, in the last class of two-body central force will be a tutorial class, and in that class we will consider more example to illustrate this concept. Okay. So, now I move to, we will consider examples, so it will be clear that time. So, I now move to another topic, the differential orbit of the differential orbit of the particle. So, now we will find a equation for differential orbit. So, what is the equation for trajectory? So, equation for trajectory. So, as you know, if a particle moves on a plane, then relation between, so plane say x y, then relation between x and y gives the equation for trajectory, equation for the orbit or trajectory. For example, if I have x square plus y square equal to a square will say that it particle will move in a circle. If I have y equal to 4ax, then we can say it's parabola. So, to find the equation of orbit, we have to find, so implies to find the equation of orbit, we need to find the relation between r and theta in this case, in this. So, let us see how we can find, and for that we have to use the equation of motion. Okay. So, let us consider the Lagrangian and the equation of motion. Okay. So, the Lagrangian, if you have not forgotten by this time, is L equal to mu r dot square plus r square theta dot square minus u r. So, this was our Lagrangian, and we found theta dot, I am just repeating these things, is del L d t del L d t, okay, and u that we have seen that it is related to angular momentum mu r square. This we have already seen because m equal to mu r square theta dot. Okay. And from here I can find that d dt, I can write d dt is nothing but d theta dt by d d theta. So, if I have a time derivative, I can convert into a theta derivative. So, it is theta dot d d theta. So, theta dot is nothing but m mu r square d d theta. So, we obtain a relation from that equation of motion from the Lagrangian, that theta dot is nothing but m mu r square d d theta. We are going to find a differential equation. So, let us box it this equation, which will be useful. Now, let us consider the radial equation. So, now let us consider the radial equation for r. So, this is d dt of del L del r dot minus del L del r equal to 0. So, del r dot, if you differentiate, it will be mu r double dot, and then when you differentiate r, you will get mu r theta dot half is got cancel, r square will be 2r. So, this is fine, and then you have the potential minus. So, minus potential will give you the plus del u del r will be 0. This is the equation for the radial equation. Okay. So, this radial equation will be using to find and using this condition connecting this, not theta dot, I am sorry, this will be d d. Okay. So, please make this correction, this will be d dt of this. Okay. So, now this equation I can write mu r double dot equal to mu r theta dot minus del u del r. Okay. And d dt I can write implies d dt, mu I can take outside, d dt of r dot equal to mu r equal to this term we can also simplify using, so mu r theta dot is mu r m square by mu r square whole square. So this will be m square mu r q. So this will be m square mu r q minus del u del r. Okay. So this is the equation, and if you take this in the other side, this was 0. So this is minus m r square this side, and that side is f r. So this will be minus, so this will be minus, so this is f of r. Okay. So this, let me correction. So let me mu d dt of r dot minus m square mu r q equal to f r. Now to simplify this equation, we'll substitute u, a new variable, with 1 over r. So du d theta will be minus 1 over r square dr d theta. Okay. So r dot, if we substitute from here, r dot we can substitute r dot dr dt. So it will be theta dot d d theta. So if you remember, we wrote d dt equation is m mu r square d d theta. So r dot will be m mu r square d r d theta. So r. Okay. So now if you substitute this r dot here, so what will obtain? Mu ddt I'll substitute here. So ddt is substitute m mu r square dd theta plus यहाँ पे r dot will be replaced by, just now I wrote r dot m mu r square d r d theta. Okay. Now if I substitute 1 over r square is dr d theta negative minus m square mu r q equal to f r. So this is the equation. So this will be mu and m mu r square d d theta, but here I can write minus m by mu d u d theta. See, r dr d theta is substituted by minus du d theta minus m square mu r q equal to f of r. Actually I should write in terms of theta. So maybe we cannot finish this lecture right now, but we can continue in the next lecture to find the orbit equation. So we'll give more time to settle this orbit equation. So let me stop here. I'll continue exactly from this equation, and I should not be in hurry to derive this equation. Okay. So let me stop here, and then I'll continue deriving the differential equation for the orbit in next class. Okay. Bye.